Okay, we have a nice long answer problem here with a few different concepts. We've got 3 parts here and then another 3 parts in a moment. So let's tackle these ones first. We have some data here regarding first ionization energies. So using principles of atomic and molecular structure and the information in this table, answer the following questions about atomic fluorine, oxygen, and xenon, as well as some of their compounds we'll get to in a moment. So, write the equation for the ionization of atomic fluorine that requires this many kilojoules per mole. So, ionization energy, we're talking about the energy required to remove an electron from an atom. And when we're talking about the first ionization energy, we're talking about the neutral atom. So the first ionization energy for fluorine means we're taking neutral fluorine, and this is the amount of energy required to remove one electron from neutral fluorine. So this is very easy, right? We've got neutral fluorine, and we're going to get F plus an electron, right? So this means we started with a neutral fluorine atom, and what we got was F plus and an electron, which we took away, right, from fluorine. So we've got F plus and an electron. So that's it. That's all this is. First ionization energy, that's what we're doing. Now we want to account for the fact that the first ionization energy of atomic fluorine is greater than that of atomic oxygen. So what we're saying here is that so fluorine and oxygen are in the same period, right? Oxygen is 8, fluorine is 9, and then we have neon, and fluorine is further to the right. So we know as we go to the right along a period, a few things happen, right? And what maybe the most important thing that happens is that the nuclear charge increases, right? So fluorine has 9 protons, and oxygen has 10 protons, right? And so that additional proton for fluorine, what that does is it causes the atomic radius to contract, right? It's a little bit smaller than oxygen. It's more electronegative, right? And so what we're understanding is that additional proton makes it harder for an electron to be removed, right? We know that the closer the closer opposite charges are to one another, the stronger the force between them. And so that additional proton, first of all, there's one more proton keeping that electron in there. So that's a greater attraction. Also, it's smaller. So the electrons are closer to the nucleus than they are for oxygen. So for that reason as well, it's harder to remove the electron. So we're talking about the discrepancy in nuclear charge, right? With the valence electrons, the valence 2p electrons in fluorine and oxygen, they feel the pull of the nuclei with differing strengths, right? And the valence electrons in fluorine feel a stronger effective nuclear charge because of that additional proton right there. All right, so we can just say really Z effective. That's the reason, right? Now, predict whether the first ionization energy of atomic xenon is greater than, less than, or equal to the first ionization energy of atomic fluorine. So here, it's a noble gas, so it's to the right of fluorine, but we're talking about the 2p subshell, 2p subshell. Xenon is in period 5. If you check the periodic table, that's in period 5. So the valence electrons in xenon are in the 5p subshell. That's 3 shells further away from the nucleus. Now, Coulomb's law, right? Again, we're saying that the farther away the electron is from the nucleus, the easier it is to grab, to take, right? The less energy that is required to take an electron because it's further away, right? As these opposite charged particles are further away from one another, the weaker the attraction. Therefore, the less energy required to take it. So because this is 3 shells further out, xenon is a much bigger atom. The first ionization energy of xenon is going to be much lower, much lower than it is for fluorine or oxygen. These are relatively high, right? These are quite high actually because we're talking about the second shell. So we're talking about valence electrons that are very close to the nucleus relative to something like xenon in the 5th period. So certainly less than. So there's a few about ionization energy. Now we're going to pivot to a different concept. Xenon can react with oxygen and fluorine to form compounds such as XeO3, XeF4, and that may be surprising, right? We're used to the idea that noble gases or inert gases do not react, but actually xenon is so big and polarizable that it can form covalent compounds. So we want to draw the Lewis dot structures here for these molecules, and they're a little bit tricky, right? And so the reason for that is that right, xenon has 8 valence electrons, right? It is a noble gas. It's got 8 valence electrons. Now the thing is, it can expand its octet, right? Anything past row 2, right? Carbon and oxygen and nitrogen, they cannot expand their octets. Those tend to obey the octet rule, but it's not so much of a rule because really everything 3, n equals 3 and later, it doesn't apply, right? Sulfur can expand its octet, phosphorus can expand its octet. We see 5 or 6 bonds around atoms like that, and xenon is even bigger. So anything that has access to d orbitals, because n equals 3 is the first, the 3d subshell is the first d subshell. So anything n equals 3 and greater has access to d orbitals. So how are they going to bond? Even though they're paired, right, we can split those up and have them form covalent bonds. So if we've got xenon there, let's put oxygen here, oxygen here, oxygen here. And we know that oxygen has 6 electrons. So let's do boom, 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 boom. And let's do the same over here. What we're going to quickly find out is that double bonds make a lot of sense, right? If we take this, if we go like this, we can do this. Okay? So this makes perfect sense because now everything is going to be neutral, right? Xenon is contributing 8 electrons to the structure. The oxygens have 2 bonds, which is what they prefer. So those are all neutral oxygen atoms. And remember, xenon is expanding its octet. So this may look like a lot of bonds, but xenon can do that. Carbon can't, oxygen can't, but xenon can. Make a note that we do have to show all of these lone pairs. So we want the lone pairs, right? Each oxygen should have 2 bonds and 2 lone pairs. It's got 6 valence electrons, so 1, 2, 3, 4, 5, 6. They have to all be accounted for. So xenon is making 3 double bonds to the 3 oxygens and has 1 lone pair left over. Right? It's got 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So that is that one. Now, xenon tetrafluoride. Now, the fluorines, these have 7 valence electrons. So they like to make 1 bond only, right? Oxygen likes to make 2 bonds because it's got 6 valence electrons. But fluorine only has 7 valence electrons, so it can only accommodate 1 bond, right? Fluorine and oxygen, they're not gonna expand their octets. Right, xenon can expand its octet, but fluorine is not going to. Oxygen is not going to. So here we see the octet, right? So xenon. Let's do this. Let's make single bonds all around. But xenon had 8 valence electrons, right? So it used 4 of them to make those bonds, and it's got 2 lone pairs left over, right? So this is what this is going to look like. Xenon's got 8 valence electrons. It's going to use 4 of them to make these 4 single bonds to fluorine, and then it'll use 2. It'll have 2 lone pairs left over, right? So that's what these Lewis structures are going to look like. Again, we need all of those lone pairs on fluorine. So now, on the basis of these diagrams, let's talk about, first of all, the geometric shape of xenon trioxide. So This is a good enough Lewis structure, but if we're going to talk about the geometry, we need to redraw this. So let's draw this over here. We've got xenon, and then what we're understanding is that this is going to look like this. Okay, this is trigonal pyramidal. Right, because this is sp3 hybridized. Right, the xenon is sp3 hybridized because it has 4 electron domains: oxygen, 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 lone pair. Right, and if something is sp3 hybridized, it has tetrahedral electron domain geometry. Right, it's got to have those 4 coordination sites. It has 4 electron domains, and here one of them is a lone pair. So it's kind of like ammonia. Right? It's kind of like we have methane, but then we have ammonia, and so we have a lone pair there. That's why ammonia is trigonal pyramidal. Here it's the same thing. It's just that we have double bonds instead of single bonds. Xenon has 3 oxygen atoms, has double bonds to these oxygen atoms, but it also has a lone pair. So that is going to be trigonal pyramidal. And then if we want to do the same for xenon, or for xenon tetrafluoride, honestly, what we have to understand is that, so here's like a little dash bond, and here's a wedge bond, and then those lone pairs are right on the top and bottom. So this would be square planar, right? The xenon and the fluorine atoms, they're all in the same plane, like this, and then we've got a lone pair on top and a lone pair on the bottom. Right, so that's how that geometry would work. But the second part is asking the hybridization of the valence orbitals of xenon. And honestly, we need to be able to understand that for both. We needed to know that this was sp3 hybridized in order to answer part 1 anyway. But over here, we can see as well, xenon has 6 electron domains. 1, 2, 3, 4 fluorine atoms, and then 2 lone pairs. So that is going to be sp3d2. If it has 6 electron domains, it needs to make 6 hybrid orbitals. So it needs an s orbital, 3 p orbitals, and 2 d orbitals in order to do that. So that's sp3d2. And then lastly, predict whether the xenon trioxide molecule is polar or nonpolar. Justify your prediction. So this will be polar because it does have a net dipole. Right? These are polar bonds. Oxygen is much more electronegative than xenon, so it is going to pull those electrons towards itself. So these bonds are polar. They're polar bonds, and it is not a symmetrical molecule. If it was trigonal planar, it would be nonpolar. But the fact that there is this lone pair here gives it that pyramidal shape, and that means that the bond dipoles all point a little bit down. If you take all those bond dipoles and add them up, you do get a net dipole that is pointing in this direction, right? So that will be polar overall. Okay, so that was a little bit. We looked at a lot of things. We looked at ionization energies. We looked at Lewis diagrams, Vesper theory, hybridization, and finally polarity. So that's a good one for these xenon compounds.